Hi everyone. Today we will going to tackle about the acid and base equilibrium. So some definition of Arrhenius. Acid is a substance that when dissolved in water increases the concentration of hydrogen ion. Base also is a substance that when dissolved in water increases the concentration of hydroxide ion. So what two ions are central to the Arrhenius definition of acid and bases? So acid is H plus and basis is OH minus. By some definition of Bronsted-Lowry, acid is a proton donor and base is a proton acceptor. So Lowry said that acid must have a removable acidic proton, and base Lowry must have a pair of non-bonding electrons. If it can be either, it is a amphiprotic. So there are HCO3, HSO, and H2O. So what happens when an acidic dissolves in water? So water acts as a Bronsted-Lowry base and abstract a proton H plus from the acid. As a result, the conjugate base of the acid and a hydronium ion are formed. So in the forward reaction, which substance act as the Bronsted-Lowry base? HSO, NH3, HO4 plus NH4. So the answer is NH3AQ. In NH3, an acid, base, or could it be both? So the answer is base. In this chapter, we learned that a more general definition for a base is a substance that can accept another proton, which is true for NH3 because of the lone electron pair on the N atom. So, more example, is H2O an acid, base, or could it be both? So the answer is both. As indicated in the equilibrium below, water is an apopteric substance that can either accept another proton or donate a proton. So another is the ion PO4 to the power of 3 an acid, base, or could it be both? So the answer is base. Phosphate is a proton acceptor, regardless of which resonance structure is being considered. So conjugate acids and bases. From the Latin words conjugare, meaning to join together. Reactions between acid and bases always yield their conjugate between bases and acid. So some sample exercise, so identifying conjugate acids and bases. So what is the conjugate base of each of the following acids? HClO4, H2S, PH4+, HCO3-. And what is the conjugate acid of each of the following bases? Cn-, SO4 to the power of 2-, H2O, HCO3-. So, sa number 1, conjugate base is a parent substance minus 1 proton. Then sa conjugate acid, parent substance plus 1 proton. So, sa number 1, sa conjugate base, so ang HClO4 less than 1 proton. Then, ang H plus is ClO4 minus. Then, the other conjugate bases are HS minus, PH3, and CO32 minus. Then the conjugate acid, so Cn plus 1 proton, H plus is HCN. The other conjugate acids are HSO4 minus, H3O plus, and H2CO3. So the hydrogen carbonate ion H or H3O3 minus is apiprotic. It is act as either an acid or base. So acid and base strength. Substances with negligible acidity do not dissociate in water. Their conjugate bases are exceedingly strong. So, using the three categories above, specify the strength of H2O3 and the strength of its conjugate base, NO3 minus. So, H2O3 is a strong acid, meaning NO3 minus have negligible base strength. So, acid and base strength. In any acid-base reaction, the equilibrium will favor the reaction that move the proton to the stronger base. So, H2O is much stronger base than Ci minus, so the equilibrium lies so far to the right. K is not measured, K greater than 1. So, acid and base strength. So, C2H3O2 aqueous plus H2O as equilibrium H3O aqueous plus C2H3O2 minus aqueous. So acetate is a stronger base than H2O, so the equilibrium favor the left side of K less than 1. So some exercise. Predicting the position of a proton's transfer equilibrium. For the following proton's transfer reaction, predict whether the equilibrium lies predominantly to the left, that is Kc less than 1, or to the right, Kc greater than 1. So HSO4 to the power of minus aqueous plus CO3 to the power of 2 minus aqueous. Equilibrium equals SO4 to the power of 2 minus aqueous plus HCO3 to the power of minus aqueous. So there is a proton's transfer reaction. The position of the equilibrium will favor the proton going to stronger of two bases. So CO3 to the power of 2 minus is a stronger base than SO4 to the power of 2 minus, because CO3 to the power of 2 minus will get the proton preferentially to become a HCO3 minus, while SO4 to the power of 2 minus will remain mostly unprotonated. The resulting equilibrium will lie to the right, favoring products, that is Kc greater than 1. So, auto-ionizing of water. So, as we have seen, water is amphoteric. In pure water, a few molecules act as a bases and a few acts as acid. So H2O is I plus H2O, equilibrium H3O plus aqueous plus OH minus aqueous. So this is referred to as ionization, auto-ionization. So ion product constant. The equilibrium expression for this process is Kc equals the concentration of H3O plus equals the concentration of OH minus. So this is a special equilibrium constant is referred to as the ion product constant for water, Kw. So at 25 degree Celsius, K water equals 1.0 times 10 to the power of minus 14. So some exercise. Calculate the concentration of H plus for pure water. So calculate the value of H plus and OH minus in a neutral solution of 25 degrees Celsius. So by definition of H, the concentration of H plus equals the concentration of OH minus in a neutral solution, we will represent the concentration of H plus and OH minus in neutral solution with X. So this gives the concentration of H plus equals the concentration of OH minus equals X equals 1.0 times 10 to the power of minus 14. So X squared equals 1.0 times 10 to the power of minus 14. So X equals 1.0 times 10. Kaya gimaynusan naman kung 14. So, ngayon mo na lang siyang 7. So, 10 to the power of negative 7 m. So, equals H plus, concentration of H plus equals the concentration of OH minus. So, in acid solution, the concentration of H plus is greater than the 1.0 times 10 to the power of negative 7 m. So, in a basic solution, the concentration of H plus less than 1.0 times 10 to the power of negative 7 m. So by Bell work, predict the product of the acid-base reaction and also predict whether the equilibrium lies to the left or the right of the equation. So pH is defined as the negative base equals negative base minus 10 log rhythm of the hydronium ion concentration. So pH equals negative log the concentration of H3O plus. So in pure water, K water equals the concentration of H3O plus equals the concentration of OH minus equals 1.0 times 10 to the power of negative 14. So because H3O plus equals because the concentration of H3O plus equals the concentration of HO minus in pure water, then H3O plus equals 1 times 1.0 times 10 to the power of negative 14 to the power of 1 half. So equals 1.0 times 10 to the power of negative 14. So therefore, in pure water, pH equals negative log times 1.0 times 10 to the power of negative 7 equals 7, because an acid has a higher concentration of H3O plus than pure water, so its pH is less than 7. So a base has a lower the concentration of H3O plus than pure water, so its pH is greater than 7.